Let's continue with example 5. A section of drainage cover 1.23 meter in length makes a howling noise when the wind blows. Determine the frequency of the first three harmonics of the cover if it's open at both ends. Take V equal to 343 meter per second as the speed of the sound in the air. So frequency of the harmony of the pipe open at both ends is Fn equal to Nv over 2L in general. So for the first harmony, we have F1 equal to 1 times 343 over 2 times the value of length to get 139 Hz for the F1. So because both ends are open, all harmonics are present. So for the F2 and F3 value, we can simply link it to Fn equal to Nf1. So for the F2, we have 2 times of F1 value, which is 278 Hz. And for F3 is 417 Hz. For question number B, what are the three lowest natural frequency of the curve if it's blocked at one end? So the fundamental frequency of a pipe closed at one end is basically Fn equal to Nv over 4L, which is different from the previous formula. So we have F1 for the fundamental is 1 times 343 over 4 times 1.23, which is 69.7 Hz. So in this case, only odd harmonics are present. Hence, the next two harmonics have the frequency of F3 and F5. So we don't get the F2 and F4 because it doesn't exist. So we have F3 equal to 209.1 Hz and F5 is 348.5 Hz. For question number C, for the cover open at both ends, how many of the harmonics present fall within the normal human hearing range? So the range given here is 20 to 17,000 Hz. Because all harmonics are present, we can express the frequency of the highest harmonic Hz is Fn equal to Nf1, where n is the number of harmonics that we can hear. So in order to get the value of n, we can have Fn over fundamental frequency. So the Fn value, we take the highest value in the range 17,000 over the fundamental value of frequency 139 to get the value of n in 122. In real world, only the first few harmonics are of sufficient amplitude to be heard. So physics of the string musical instrument is actually quite simple. So the note play depends upon the string which is disturbed. The string can vary in length, tension, and linear density. For example, fingers are used to change the length of the string over here because different string linear density, so we can have the belly of the instrument acts as the amplifier. So next we have this kind of a musical instrument whereby we have the open end over here and the mouthpiece open end at the top. So the open end at the top is the air is blown across the mouthpiece, and the finger lift the keys to change the length of the tube, which means we can change the frequency of the note. For this type of musical instrument, which is open tube type, so the finger covers hole to change the length of the tube, whereby we can change the frequency of the note. Next, we have the resonance in A column. So we have the A column, we place it next to the loudspeaker, and the loudspeaker is connected to the audio frequency generator. So the loudspeaker emits sound of a certain frequency which can be changed. So the vibration of the diaphragm of the loudspeaker forces the air in the tube into vibration. When the frequency of the vibration of the loudspeaker equal to the fundamental frequency of the A column, so the resonance will occur. A sound of high intensity, perceived by ears as the loudness, is produced at this frequency. So next we have our last subtopic 10.5, dropper effect. So have you ever experienced this? You may have noticed that you hear the pitch of the siren on a speeding fire truck drop abruptly as it passes you. Or you may have noticed a change in pitch of a blaring horn on a fast-moving car as it passes by you. Or even the pitch of the engine noise of a race car changes as a car passes an observer. So when the source of sound is moving toward an observer, the pitch of the observer hears is higher than when the source is at rest. When the source is traveling away from the observer, the pitch is lower. This phenomenon is known as the Doppler effect and occurs for all types of waves. So the definition of the Doppler effect is defined as a change in the apparent frequency of the wave as a result of relative motion between the source and the observer. So explanation of Doppler effect phenomenon. First one, when observer and source are both in stationary state, whereby V equal to 0. So there is no relative motion between the source and the observer. All observers hear the same frequency because based on the formula V equal to F lambda, when the speed is constant, both the lambda and the F also constant. Second case, the movement of the source alters the wavelength and received frequency of the sound, even though the source frequency and sound velocity remain unchanged. So, as the source moves away from the observer, the same number of waves are expanded to fill a larger distance. So from the equation V equal to F lambda, when our V keep constant, frequency is inversely proportional to wavelength. So when our wavelength increase, frequency will decrease. That's why the observer will hear sound of longer wavelength with lower frequency and lower pitch. As the sound source approaching the observer, the same number of waves are compressed into a small distance. So according to the same formula, V equal to F lambda, when V is constant, frequency is inversely proportional to wavelength. So as our wavelength decrease, frequency will increase. So observer will hear sound of shorter wavelength but higher frequency and higher pitch. This is the general formula used to describe the apparent frequency, which is Fa stands for the apparent frequency or observed frequency, equal to, in bracket, V, the speed of the sound in constant list, plus minus V naught, the speed of the observer, over V, still the speed of the sound in the constant list value just now, plus minus Vx, means the speed of the sound source, multiply with the frequency of the source or the actual frequency. So here we can have an alternative way which we apply the OS method to get the correct positive or negative sign to fill in the general equation. So basically we have to write the negative at the left hand side of the O and positive at the right hand side of the X. So we have an example here on how do we apply this OS method. So let's say we have moving observer approaches stationary source. So we have observer approaches the stationary source. So we can have positive sign at the top. So we have Fa equal to V plus V naught over V. The value of Vx actually is 0. So times the value of frequency of the source. So next one, we have moving observer receiving stationary source. So for this one, we have negative sign to put at the top, whereby we have Fa equal to V minus V naught over V, our Vs still 0, times F. So next example, moving source approaches stationary observer. So we can use the arrowhead, approaches the observer. So we still get negative. So we have Fa equal to V whereby our V naught is 0 now, over V minus Vx from the sign given. And the last one, moving source visiting stationary observer. So visiting stationary observer, we have a positive sign to get. So we put into the equation Fa equal to, in bracket, V over V plus Vx multiplied with the actual frequency. This is a graph showing the apparent frequency against distance travel. So basically we have F for the actual frequency, Fa for the apparent frequency. So as the source moves closer or approaches the observer, we have Fa greater than the actual frequency, so mean higher value from the F. And this is the arrowhead showing it approaches the observer. At the moment source crosses the observer, apparent frequency will be equal to the actual frequency at this point. Fa equal to F. Next, as the source moves away from the observer, actual frequency is greater than apparent frequency. So actual frequency greater than the apparent frequency as our source moves away from the observer. Next, we have the example 6. The siren of a police car arrests amid a predominant frequency of 1600 Hz. What frequency will you hear if you are at rest and the police car moves at 25 meters per second towards you? Given that the speed of sound in the air is 345 meters per second, we can also apply the OS method just now, whereby we can get the negative sign to put at the bottom here, and our V naught is 0. So we can have Fa equal to V over V minus Vx in bracket multiplied with the actual frequency value. So we substitute the value of speed of sound 345 and the sound source value 25 and multiply with the frequency 1600 to get the Fa value is 1725 Hz. So here is the end of the topic 10. Hope you can understand the video. Thank you for watching.